Welcome to South Windsor High School, the home base of FRC Team 177. This is where we as a team design, build, and test our robots for the first robotics competition. My name is TJ Watson, and I will be your guide as we travel through the design process. Along the way, I will introduce you to our unique team culture and show you how the Bobcats do robot. The Bobcats take a systems engineering approach to our robots in the design process. This means that we spread the workload across a series of sub-teams and organize the flow. Now, the four sub-teams are CAD, Mechanical, Electrical, and Fundraising. The CAD sub-team is responsible for creating virtual versions of the robot, which can be used to make parts and make large design changes without wasting expensive building materials. The Mechanical sub-team is then responsible for prototyping, machining, and building the robot itself. The Controls team is responsible for wiring and programming the robot that the Mechanical team builds. Another element of the team includes fundraising, which raises funds for the rest of the team and coordinates trips. These sections are held together by the team leaders and also the mentors, which keep the whole process running smoothly. None of the sub-teams would get the job done without the others, so teamwork is essential. This process has been very successful for us and has led us to 2 different championship wins. We've actually spread this idea throughout several other first teams. We mentor at least 2 teams this year, including 2468, who we helped develop their elevator, and 3555, who we actually help with startup and things like that. I even took this process and used it to create a new VEX team for our school. After all, being a part of FIRST is about spreading the ideas of gracious professionalism. Let's get started. The first step is to define the problem. Luckily for us, FIRST gives us our problem in the form of a game, which comes with its own handy book of rules and regulations. This year's game is Logomotion, which contains an awesome twist.
Near the end of the match, robots drive to the towers and deploy minibots on the tower poles. As the endgame starts, minibots race to the top of the towers. The first minibot to the top earns a 30-point bonus.
Our problem statement then becomes to design, build, and test a miniature robot that climbs the pole as fast as possible. Brainstorming and research occur simultaneously as everyone works together, forming images of what our robot should look like. We were given a list of constraints that has evolved as the first teams from around the world have begun grilling the game design committee. The minibot must fit within a 12-inch cube, and it must weigh less than 15 pounds. In addition to that, it can only be made of certain materials, and you only have 6 weeks to build it, plus the time until your first regional. With our heads wrapped around the design challenge, we decided it was time to move forwards with the exploration phase. This is Minibot Not. It's the first prototype minibot that we built that tests the cantilever type design, where we use this battery to give us friction against the pole. Now, as a prototype, we learned a lot from it. For instance, we learned that you can't drive this bottom wheel, because if you drive it and it's hugging the pole like this, then it'll drive this wheel up and you'll lose your friction and the robot will fall down the pole. The next minibot is called the Mark I. It is essentially a copy of Minibot Not, only made out of Tetrix parts. Using what we learned from the prototype, we changed the original design to include a chain drive to the top wheel. In testing, the minibot had trouble staying on the pole, even when we added a magnet to help hold it on. After we had trouble staying on the pole, the next innovation was a latching system. As you can see, the Mark II would include guide rails to ease deployment. The other innovation in this design are the latches. See, the latches spin only in one direction. They allow the minibot to pass into latching position, but do not let it unclasp the pole. For testing purposes, we added tension to the wheel with zip ties, and got an acceptable time, getting to the top in 4.5 seconds. Exploration of the Tetrix motors revealed a gearbox that we could make use of. The Mark III changes the reduction to a 10.4 to 1, using the pre-existing gears from the gearbox. This is a more ideal speed for us, and uses one less gear, meaning that it's more efficient. We also no longer needed the bands to hold tension on the wheel. When we finally tested this minibot, it climbed the pole in 3.05 seconds. This time is perfect for our purposes, and we may be able to optimize the weight for even more speed. Now think back to the design process. What was that final step?